again here in the channel. Together with me and Michael, who you've seen before, is Laurence Barker, Golf 8 November Juliet, who's in the moment about 10 miles north of Portsmouth in UK. And I have the honor to present Laurence to you. Laurence is an experimenter and a developer, and he's been doing a few SSP contests with his friends, but he also likes to dabble with amateur radio, high frequency research, and he's made a prototype radio using a red pitaya board. And he's been working with Kjell Carlsen quite a lot, who we see later in the conference. And he wrote the software for the Odin front panel controller, which was presented at SDRA 2018. And since then, that's 2 years back in time, this has been extended into a front panel for the new radio called Andromeda. And he's written the software for a new automatic antenna tuner called Arius that integrates with HPSDR radios, and is slowly developing he's slowly developing a Xilinx FPGA based SDR module for this environment. So we're going to listen to Laurence's talk, which has been pre-recorded, but he's already here in our channel. So we will be monitoring your chat contributions also during his talk right now, and afterwards we're going to come back and we're going to have a little chat together with you, and we will respond to your questions, which you can already now post in the chat. So thanks for contributing already now, and let's blend over to the video.
Okay, good morning. I'm Laurence Barker. I'm going to be talking to you today about how to use the Xilinx Vivado tools for doing SDR development in Xilinx FPGAs. I'm going to be going through a few things. First of all, I'm going to start with what you will find in the typical software-defined radio field programmable gate array. So what kind of functions are in there? I'm going to create a simple transmitter using Vivado's IP Integrator. I'm going to go through how we debug that with the simulator. And finally, I'm going to run that on the hardware. And then right at the end, we'll have a very quick look about what the differences are in the receiver. So let's start with why am I doing this? I want to have a radio where I've written some of the code in it. I've always been interested in software-defined radio, and I wanted to understand what the algorithms that are typically used are. And I haven't designed an FPGA for 25 years, and when I did that, the tools we used were quite different. This is going to take me several years to learn. I'm only 3 years into this, so it's not going to finish just yet. I want to say at the start that I haven't done anything particularly original here. I've learned from all of the others. I learned about how to use the Vivado tools and what the software-defined radio blocks might be from Pavel Demin's design on the red pitaya. I've learned some of what the flow graph is in the HPSDR family from Phil and Warren's work and others. I apologize to anybody that I've missed out from that. So what do we find in a typical HF software-defined radio? Well, I've drawn a little diagram here. On the left-hand side, we've got the RF part. On the receive path, we have some filters that will typically filter one or several whole bands. And then the A to D converter will convert nowadays the entire HF band, so maybe DC to 52 megahertz. That data goes into the FPGA. On the transmit path, the FPGA gives the samples out to the D to A converter, and you then have a normal linear amplifier and low-pass filters. The FPGA you can think of as being the glue that sits between the RF part and the application that runs on your PC. It's got to reduce the signal center frequency down to 0 center frequency. It's got to reduce the bandwidth to get to a rate that you can transfer the data to a PC. And then it's actually got to do the data moving, usually on USB or nowadays Ethernet. That data then goes into your PC and you run a program. Power SDR and HPSDR are examples, and most of the signal processing complexity is in there. There's a huge amount of code in there. It's got to select the signal, it's got to modulate or demodulate it, it's got to provide you a user interface and your spectrum display. That's where most of the effort is. If you want, you can still have a front panel connected to that with knobs and buttons. And 2 years ago, we described the Odin front panel controller at this event. One way that you can make that is with a red pitaya. It's quite a well-known board, and it's going to be described at this event again. The red pitaya has got A to D and D to A converters on it at appropriate sample rates for signal processing or HF signal processing. I think the 125 megahertz sample rate. And it's got a Xilinx Zinc FPGA. That's what's called a system on chip FPGA that I'll say a bit more about in a moment. And it's kind of a cross between an FPGA and a single board computer. So on the other side of the FPGA, we've got an Ethernet interface where the data is transferred out to your PC application. Another way to make it is to look at a different type of module. I've got a couple of examples here. These are called system on module boards. They're more like a single board computer than they are like a radio. So they don't have the A to D and D to A converter on them, but they do have connectors that will connect to those. But the two boards that I've shown there also have video interfaces and all of the rest of the interfaces that you need to have a single board computer. So what I'm trying to do is to make a radio that runs on that. The display will come out from that Xilinx Zinc FPGA. The mouse and the keyboard will connect to that, and the front panel will connect to that. So the system on chip FPGA is what enables this to happen. You can think of it as being two halves. In the left-hand half, we've got the processing system. That's made from either 2 or 4 ARM processor cores. And it's got the interfaces that you would expect for a single board computer. So video, USB, Ethernet, serial, things like that. Typically connected to a reasonable amount of dynamic memory. On the right-hand side, we've got the programmable logic part, which is the conventional FPGA. That's made from 3 things. It's got a lot of logic, it's got a reasonable amount of block memory, and it's got some signal processing resources, basically multipliers and adders. The chip that's on the boards that I described has got roughly 2 million gates of logic. That's more than you're ever likely to need in an HF SDR. Nearly 1 megabyte of block memory and 360 DSP slices, and that's enough to do the job. Finally, at the right-hand side, it's got I/O signals to which we can connect the A to D and D to A converters and all of the strobe lines that we need for transmit, receive, filter control, and so on. Very quickly, I'm just going to say something about the overall design flow. Your design consists of the 3 things at the left-hand side. At the bottom in blue, we've got the FPGA, which is the bit that we're going to be describing today, and we use the Xilinx Vivado tools to create that. At the top in green, we've got the SDR application, for example, HPSDR, which we can create with just conventional C compilers and things like that. And that ultimately ends up with an executable file. In the middle, we've got the Linux operating system, and sometimes you have to build that, and the code from your FPGA design will have to be merged with that. If you're lucky, your single board computer suppliers might have done that stage for you. That's still a stage that I don't really understand. All of the files from those 3 design flows all end up on an SD card plugged into your system on module board, and it then executes. There are 3 ways to design the FPGA. One way is to write the VHDL or Verilog code by hand. That's something that you can do. It's quite a lot of effort to do that, but at the end of that, you've got total control over your design. Nobody is getting in your way, and there's no constraints that you didn't put there. The bottom way that I've described is to synthesize the FPGA from a higher level language. Xilinx provides tools to synthesize FPGA code from either C or Python, and MATLAB and GNU Radio provide code from which you can synthesize the FPGAs. That might well be the way of the future. It's not really the way that's most common today. But an interesting challenge might be, could we port some of Warren Pratt's WDSP algorithms so that we could take the signal blanker and then the spectrum display parts of the code, run those on the FPGA and free up the ARM processors to just do the audio processing? I don't know, but it'd be interesting to try. The approach I'm describing today is essentially where we take somebody else's intellectual property in the form of blocks of parts of designs and join them together. If you remember designing TTL logic, we used to have a TTL data book. It's a similar kind of principle. All I'm doing is reusing good designs. So what needs to happen in that FPGA? We start off at the left-hand side with an A to D converter that's going to take samples of the input signal at quite a high rate. 122.88 megahertz is common. Let's just imagine we're looking at the 20 meter band and we're interested in an SSB signal at 14.205 megahertz. Well, the first thing I need to do is to down convert the HF band to a zero center frequency. So I need a digital oscillator that perhaps I might want to set to, that's like your VFO, and I might want to set it to 14.2 megahertz. That's then going to mix the signal down, and we use the sine and the cosine of the local oscillator to give us two representations of the signal at zero center frequency. We call those the in-phase and the quadrature channels. And what we've got now is two channels that we have to low pass filter them to define the bandwidth, hugely reduce the sample rate in a process called decimation, and then transfer the data to the PC. So our 14.205 megahertz SSB signal has now been reduced to a signal at 5 kilohertz in those two channels. To do that, the blocks that I'm going to use are these ones. My VFO is implemented with a thing called a direct digital synthesizer, which is going to give me the sine and the cosine of the local oscillator. The mixing process is done with a complex multiplier, which is going to multiply and then give me a complex output signal from which I get the in-phase and the quadrature parts. The filtering I'm going to do in two steps. First of all, using a cascaded integrator cone filter, decimating by 320, and then an FIR, but decimating by a further factor of 8. Those design decisions were made by the HPSDR project. The reason is the CIC filter has a huge roll-off that you would otherwise have to equalize, but if you decimate by 8 or 16 in your FIR filter, you can kind of ignore it. I've then got a low pass filter. I've selected a bandwidth of 0 to 22 kilohertz, which gives me a total bandwidth that the PC will see of plus or minus 22 kilohertz, or 44 in total, with a 48 megahertz sample rate. Before we start looking at the FPGA, and before you start using any of the tools, you really ought to look at some information from elsewhere. The Xilinx User Guide 995 is a really good tutorial of how to use the IP Integrator, and it will go through some examples. It would be a really good idea to read that. It's not particularly long. And I've listed there some other sources of information that I've used. The Zinc book was quite useful to understand the overall process and essentially what the FPGA chip is. You can also get all of my design files for this example project off of GitHub. First thing that you'll need to do is to download and install Vivado. The Webpack edition is free to use for the smaller devices, and by smaller they seem to mean devices with less than about 5 million equivalent gates, so they're going to be big enough for these purposes. Xilinx produce a new set of tools every 6 months or so. The current version is called 2019.2. You can't just upgrade to the newest one. Your design is tied to the tool that it was created with until you go through an upgrade process. And that upgrade process isn't guaranteed to work, or might at least need a lot of effort. So you could end up needing 2 or 3 versions of the tools installed. And they're typically 50 gigabytes each. So you might want to think about how much disk space you've got available. You also need to decide how and where you're going to run them. I run Vivado on in a Windows environment. The better Linux tools have to be run on Linux. I'm using a Ubuntu virtual machine that runs on the Windows environment, but you could run the whole lot on Linux if you wanted to. To be able to download the code, you need to create a Xilinx account, and then you can download and run the installer. The product that you need to download and install is actually called Vitis. And the key step that you need to take when you go through the install process is tell it not to load a license manager. So for the free devices, it will work absolutely fine. When you run Vivado, you end up with this main screen. At the left-hand side, you've got the main design steps. So from the top to the bottom, if you click on those buttons, you will go through the main processes that you need to make the FPGA. There's a section to the right of that that shows the source files in the design, and then there's some project information shown to the right. That depends what stage of the process you're in. And the bit at the bottom right is usually messages from the various design tools. The part of the tool set we're going to use is called the IP Integrator. And all of my work with Xilinx so far has been done using the IP Integrator. This is where Xilinx, or for that matter somebody else, creates the intellectual property and creates these blocks. And what we then do is to join those blocks together in a block diagram. Creates a visual form of the design. And there's 3 reasons why I think that's a good thing to do. First of all, it was quick to learn. So you don't have to learn a language. Essentially, if you're used to designing hardware, it's an environment you'll recognize immediately. It's just like a schematic. At the end of it, once you've joined your blocks together, the code works. But the really good advantage that I find to it is you've got a block diagram that shows what the code looks like. And it enables other people in the design team to understand what that code is. And that can be quite powerful when those people can't read all of the software. To start an IP Integrator design, you click on Create Block Design and you get a design canvas as is shown there. And it's just like a schematic editor to which you can add IP blocks, which are those cores. You can add modules, and you can create modules are essentially small pieces of Verilog. And you can create ports, which are the input and output signals. And then you just join those together with wires. We'll give an example in a moment. If you look at the blocks that are available, there's around 180 in total. There's various forms of processor. There's quite a lot of signal processing resources. There's all sorts of video and display drivers. There's a large number of interfaces, for example, USB and Ethernet and serial and others. And then some infrastructure. These are the kind of blocks that everyone will end up needing somewhere along the way. They're all joined together with standardized interfaces, and that's really what's made this whole process work. Because they have standardized interfaces, if somebody creates a block into that overall library of blocks, it will work with others. There's a lot of DSP functions available. It's got all of the functions that we need to make an HPSDR and quite a lot more. If you wanted to make yourself a 4G base station, most of the signal processing you would need is there. If you want a fast Fourier transform, it's there. There's memory and there's FIFOs and quite a lot of other DSP functions. Let's look at the I/O signal, because it's worth having a look at these, because we will need to understand them. I've got the FIR filter here, and it's got three things on that. It's got a clock, it's got a stream of input samples, and it's got a stream of output samples. And the output sample rate can be the same as the input, or it can decimate, which reduces the sample rate, or it can interpolate, which increases the sample rate. Whichever of those it does, the input and output comes out on what's called an AXI stream. This is a standardized way of passing streams of data. Essentially just a continuous stream of data on a single parallel bus. That's what makes the signal processing really easy. The signal processing blocks take that standardized stream and they just join together. It's worth having a quick look at that just to see what is involved. The AXI stream, there are more signals available for more complex operation, but in its most common form, it's got three signals. It's got a bus called T-data, which is essentially a pipe of those samples, which can be several bytes wide. It's got a signal called T-valid, which is a signal from the originator of data, called the master, to say, I am ready to transfer data. And it's got a signal called T-ready, which comes from the receiver of data, or the slave, which says, I am ready to accept data. And data transfers when both T-valid and T-ready are both 1 in the clock cycle. All the devices are clocked at the same speed, and T-ready and T-valid between them means that the data will only flow when both the source is ready to send data and the recipient is ready to provide it. So one of these AXI streams connects between just one source and one destination, and can't connect to multiple devices. So it's literally just a piece of string between two blocks. Before we start the FPGA part of the design process, we're going to need an FIR filter, and we've got to calculate its coefficients. And the Xilinx tools don't help me with that. I found a filter design program called T-filter online. I'm after a filter that's got a sample rate of 384 kilohertz and a pass band covering just 0 to 22 kilohertz with a small amount of ripple. And the stop band from 24 to 192 kilohertz, I want to be down at minus 140 dB. So you specify those into just a tiny spreadsheet on the design form, press the button to calculate the coefficients, and maybe 5 minutes later, it gives you a coefficient set for your filter. Mine's got about 950 coefficients. And you can copy those from there. I've pasted them into a spreadsheet and used that to do a very slight format conversion to get the file into a format that the Xilinx tools will accept. That's all in my GitHub repository if you want to look at it. So what we're going to show now is a quick video that goes through how to connect the design up using IP Integrator. And I've gone through the process of creating a simple transmitter and joining the blocks together. Then once the video's finished, we'll come back and see how to go through and simulate that design. Okay, this is the IP Integrator. Essentially, it's a design canvas where we drag blocks onto it and we join the blocks together. To get blocks onto it, you click on the plus button and it gives you a list, and you just click the block that you want and drag it on. I've already added the blocks that we need, and I've set all of their properties. To set the properties, you double click them and then pick them from a list. I'll talk them through as we go. This is the FIR filter. This is going to take IQ samples from your SDR application such as HPSDR. So 16-bit INQ input, and it's going to interpolate the data from 48 kilohertz to 384 kilohertz, so a factor of 8. FIR filters are quite an expensive resource. They have a lot of multipliers, so we're going to do something slightly clever and reuse that filter. So we'll use the same filter for each of I and Q. To make that happen, we use a thing called an AXI data width converter. That's essentially a multiplexer, so it will take in an AXI stream with 4 bytes of IQ data, and it will give out an AXI stream with 2 bytes of data at twice the data rate. That will connect to the FIR, and on the output of the FIR we get now 3 bytes of output data at twice the required rate, and that will go through a demultiplexer in the other data width converter to give us 6 bytes of output data at the 384 kilohertz rate. To join them up, you just hover over an interface, a pencil appears and you drag. Hover, pencil, drag. To connect up the clocks, hover, pencil, drag. Hover, pencil, drag. Hover, pencil, drag. That's connected that up. Don't worry about where the wires go, it will change that, and you don't have a lot of control over it. The next stage is we're going to go to the CIC filters that will convert the data to the final 122.88 MHz sample rate that we need for modulating the local oscillator DDS. There's 2 scalar filters, one for in-phase samples, one for quadrature samples. So to get 2 separate AXI streams, we use a thing called an AXI stream broadcaster. This takes one AXI stream and gives 2 separate output streams, and I've set it to pass the first 3 bytes to that stream and the second 3 bytes to that stream. So in-phase samples to one, Q samples to the other. There's no extra data, it's just split them up into being separate streams. Again, hover, drag, hover, drag, and that's all of those connected up. Let's just connect up the reset, and our CIC filters have got their input data. The CIC filters are going to interpolate by 320 to give me the final output sample rate, and the data then comes out on these separate AXI streams that we now need to combine back together again. So we start off with a separate I stream and a Q stream. An AXI stream combiner will then give me a single stream, twice the width, but it's a single IQ quadrature stream. Again, hover, drag, it doesn't matter whether it's source to destination or the other way. That's got everything connected up. The output now here is the modulated signal. That is ready to modulate the DDS. The DDS is providing the samples of the local oscillator. I've set that to be 122.88 MHz clock rate, and to provide a frequency out that depends on an input frequency word. I've set all of the parameters, so I'm just going to connect that up. The complex multiplier takes in 2 complex numbers and gives out a complex number. That gives the final D to A output signal. Again, connect up the clocks. On the output of the complex multiplier, we now need to connect the I or the Q, it doesn't matter which, to the D to A converter. I've got a couple of little bits and pieces here. The first is what's called a slice. This is essentially just a bus ripper, so I'm going to use it to take the 32-bit IQ value from the complex multiplier to give me a 16-bit just an I value. Connect that up, and the last thing is a little bit of Verilog this is a module which is going to convert it from signed magnitude to offset binary, assuming that's what your D to A converter requires. It depends on what your D to A converter is. That's connected to a schematic port, and that's then ready to go to output pins or to the simulator. By connecting it to a port, it's visible to something off the page. That's all the signal processing done. The last things that we need to do are to put a frequency in there. We've got to put a modulating signal in there, and we've got to connect up the clock and the reset. So there's a few extra bits over on the left hand side. To give me an IQ signal for simulation, I've just added another DDS that's set to give a constant 10 kilohertz signal. So I'm just going to connect that up simply. We need to give clock and reset to everything, so there's a little bit of IP that generates a synthetic clock for simulations. No good for testing, it's only any good for simulation. That's set to give the right frequency and a reset width of 200 pulses. And to connect the frequency for the DDS, I've got an extra little bit of IP, which is written in Verilog, which just takes an input bus of 16 bits, the frequency word, and it's going to convert that to being an AXI stream ready to go to the DDS, which I then need to drag down to the DDS. And that is our schematic connected up, all ready for simulation. Okay, we've got our complete block design. Anyone who spotted the deliberate error can tell me at the end. Now we're ready to simulate that. It's quite a simple process. We save and close the block design. There's a very simple process to create what's called an HDL wrapper. That's what is needed to make that block design available to the rest of the tools. Then you click on the left-hand side of that diagram, run simulation. And if you do that, it almost certainly won't work first time. So instead, I'm going to show you how to break the design up into small sections and test each, and how to add debug to it until you get to the point that it works. Behavioral simulation is how we do almost all of the debugging. You don't try and do it in the FPGA itself. It takes too long, and the process per step is just too slow. In the simulator, you've got access in principle to all of the information. You can add debug signals to any part of the design. You can access everything in the simulator. Any signal that you've put on as a port on that block design is available in the simulator. And you get a list here. If you want to view a signal, you drag it from there onto the simulator page itself. If you need to force a value onto the input, you right-click the signal in this pane and select force constant, and you can force a new value to it. And on the toolbar, there's run and pause buttons, just as you'd have with a video recorder. So let's start off simulating the DDS. This was the basic DDS part from the design, connected to the Verilog source at the input. I've connected its output via a couple of slice IPs, each of which takes half of the output data. So this takes the first 2 bytes, the in-phase part of the data, to go to the D to A converter. This takes the quadrature part, so the second 2 bytes. They're connected to ports on the design canvas. You then click run behavioral simulation. You can drag those 2 buses onto the screen, run the simulator, and we get our nice sine wave. We've got 2 sine waves there, both in quadrature, and we can see that the DDS is working properly. I've got that set with a frequency word of 0042 AAAA. That corresponds to 1 megahertz. Now we can add in the complex multiplier. So this was my DDS, and these were my output slices. In between them, I've now put the complex multiplier. The output data width has gone up a bit because the complex multiplier increases the output sample size. So I've got to change the size of these and the size of the ports on the schematic. And we need to add another DDS compiler as a test source. Ultimately, the modulating signal will be coming in from a PC as an IQ signal, but as a quick way of getting going, I've added another DDS set to 0.5 megahertz, instead providing a different IQ signal. When we run the simulation, we now get sine waves to the frequency of 1.5 megahertz, which is what we expect. That was 1 megahertz from there, phase modulated by 0.5 megahertz from there. So we can see that the complex multiplier is working correctly. I've now added the filter chain in place of that DDS. That is the complete FIR filter followed by the CIC filters. that the output of the AXIS combiner then feeds into the mixer. And I've moved that test DDS feeding data into the FIR filter. I've now set it to a sample rate of 24 kilohertz and set it to produce an IQ signal of 10 kilohertz. You could have broken this down in 2 stages. It's a good idea to do this in 2 stages and feed the signal into the CIC part first, and then finally add the FIR as a second activity. When we do this and we run the simulation, we now got essentially 2 separate halves to what we're simulating. We can look at essentially the sine waves that come out at any part of the process. But they're at hugely different rates. So what I've done, I've set the VFO DDS to 0 hertz. So when you run the simulator, we've got the 10 kilohertz IQ signal modulating a 0 hertz local oscillator, which gives us 10 kilohertz out. You need to be patient. The filters have a settling time of about 2 milliseconds, and to calculate out 2 milliseconds of simulation takes several minutes on my PC. But after those several minutes, we get our sine waves out, and there we are. We've got the I and the Q signal ready to go to a D to A converter. To see the effect of the local oscillator, if you pause the simulation, change the DDS input word using the force constant to that value there, and then continue the simulation, you'll see that all of a sudden the output sample rate is hugely bigger. And if you zoom in on that, there's a little zoom in button up here, you'll find that we've got the sine wave that you expect, which is now very slightly more than 1 megahertz, 1.01 megahertz. It's hard to tell that that's 1.01 megahertz rather than 1.0, because all you're doing is essentially looking at a sine wave. You can zoom in and find the 0 crossings carefully, but it's actually quite hard to spot. Trust me, it is. So that's our basic transmitter working. The last thing that we need to do now is connect that to a real D to A converter. I've used a tiny bit of Verilog here to convert to offset binary format from 2's complement. All you really need to do is invert the top bit. But to invert the top bit, you'd have to rip out the top bit and the remaining 15 bits, invert that bit, then combine them together, and you end up with a bit of a mess in the IP integrator. A simple bit of Verilog, it's only a couple of lines of code, is instead another way of doing it. You can do either. I've then connected that to a D2A converter that I've just made from an R2R resistor ladder network. The other thing that we need to do is add a real clock and a real reset signal. Well, you can get those from the ARM cores in the Xilinx Zinc devices. The ARM cores give out a 100 megahertz clock signal, and I've used a PLL clock multiplier to increase that to 122.88 megahertz. It's all right for testing. It wouldn't be any good for a radio because it's got way too much jitter. You need to connect that to I/O pins, generate a bit stream, and you can then use a JTAG interface to download that into the FPGA. On a Xilinx Zinc device, you also need to be running code on the ARM processors themselves, so you have to create a little Hello World application, but the Xilinx tutorials will tell you how to do that. So there we are. That's with my oscilloscope connected up to my D2A converter that's made out of those resistors. That's running on my Ultra 96 board, and there's the sine wave we get, and the oscilloscope has measured the frequency as 1.01 megahertz, which is exactly what we expect. That's not bad for an 8-bit converter made out of resistors. I don't imagine it would work too well at 50 megahertz, but it's done the job to prove that the hardware is working. Let's very quickly look at how a receiver is different before we finish up. Obviously, the flow graph is the other way around, and that's what I described when we began the talk. The DDS would have to have a greater dynamic range. Typically, you'd set it to generate something like a 140 dB spurious-free dynamic range. Just increases the number of IQ output bits. Commonly nowadays, you have several receiver channels, not just one, so that you can be operating several receivers, and it's common to have 2D to A converters. Sorry, 2A to D converters, so you've got two entirely independent analog RF inputs. Also, the output sample rate is usually higher. None of those are actually a very big change to the design. So in the IP integrator, this is roughly speaking what you would end up with for a flow graph for a 4 receiver with 2 A to D converters. Each A to D converter is connected to an AXI stream broadcaster to send 2 sets of its samples out. You make yourself a simple receiver block with the DDS and complex multiplier and the cascaded integrator cone filters. The CIC filters don't use very many resources, so it's not a problem to have lots of those in your design. And we end up with now 4 pairs of IQ output streams from the CIC filters. You combine all of those together with an AXI4 stream combiner. That's like what we did before. It's just a bigger combiner with more inputs. And we use an AXI stream data width converter, just as we did before, just with the parameter set, to convert from 24 bytes in down to 3 bytes out. That goes through an FIR filter, and the output of that will write into a FIFO memory, which is then read out by the PC. To get a 384 kilohertz sample rate, your CIC filter needs to decimate by 40, and the FIR will decimate by 8. So the FIR filter sample rate is a bit over 3 megahertz. But all of the designs that were on that design canvas, if you just take those same blocks, reorder them, change some of the properties, you can make that receiver in quite a small space of time. Go through the same process as I described, and you can debug it and get it working. So what have I learned from doing this? Well, the DSP in an FPGA isn't anything like as hard as I expected it was going to be. You need to know what the blocks are, and you need to join them together properly, but you go through that joining process and learn how the blocks join together and how to debug them, and you'll get there. It's actually quite hard to simulate the whole system in one go. It's much better to break the thing up into smaller designs and simulate smaller parts of the designs before you bring them all together. So simulate a single channel receiver, part of your transmitter, then bring them slowly together to build up. It's quite hard to simulate in other tools the combined CIC and FIR filter. If you've got MATLAB, I expect it's quite easy. For non-professional users, that's not available. I have wondered if I should write a CIC block for GNU Radio so that I can simulate in a PC type design environment that combined process to see the overall filter shape. You need some other things in the FPGA. You've got to interface to the PC. You've got to provide various strobe signals. You might have to connect an audio codec and need a CW gear. Break it into chunks, take on one at a time, and you'll get there. I've still got a long way to go with the Linux side of it. So if anybody knows how to port desktop Ubuntu into one of those Zinc system on chip modules, please talk to me, because I don't know how to do that yet. So in conclusion, we've gone through the very basic processes of how we use those tools. We've made a simple transmitter, and we've simulated it and run it on an FPGA. And if we connected the IQ data into that from the PC at the left-hand side, that would have worked. We've looked at what needs to be in the receiver. Do get into these tools, download them and try them out. It isn't as hard as you think to get started with it. And the boards such as the Redbita are readily available to work with. So that's the end of my presentation. My design files are on GitHub if you want to look at them, and we'll be happy to answer any questions. So thank you everyone for listening.
So, okay. Laurence is also here with us here in our conference room again. And we have seen his presentation, highly interesting presentation, which we've recorded a couple of weeks before. So in parallel to that, there has been quite a discussion in the chat function of the video channel, and we've been following that. And Markus Müller was raising quite interesting questions or commenting quite a lot, and also a user called Quadrant 2005. And yeah, the discussion's been going on mostly between these two contributors. And Art Thomas is also here, who's going to speak to us later. Okay, Laurence, you follow the discussion also. Would you want to comment on one of those contributions or several of those contributions?
Yes, thank you. First of all, thank you everyone for watching my presentation and listening to what I have to say. So it's good to know that it's generated some interest. One of the questions seems to be about what processing should be in the FPGA versus what processing should be in the microcontroller or the ARM core. And there's a question to which there is no right or wrong answer. Some people will prefer to do more of one or the other, but either will work. And as somebody observed, you get the same numbers at the end, whichever part of the processing system you use. The FPGA is really good for low latency processing, and particularly for constant latency processing. So if you're receiving a new sample every clock from an A to D converter at 122.88 megahertz rate, you can't take that straight into a processor. It's got to be handled with something else. That's the kind of thing that the FPGA exceeds that. Conventional processing is much easier to write the code. It's much easier to debug the code, and it's very familiar to people. So the processor side is good for familiarity and where you need a lot of code. In terms of the amount of code that's in the FPGA, though, if you look at the total flow graph for your overall HF SDR based radio, only a tiny part of that sits in the FPGA the way I've coded it. At the moment, what we tend to do is have the kind of audio bandwidth processing done at the PC end, and we hand off samples at a rate that's suitable for that to the PC or the processor. So somewhere between 48 kilohertz and maybe 1.5 megahertz. And for the audio processing side, 48 kilohertz is fine. For having a spectrum waterfall display and so on, you might want to see a bit more of the band than that. So from the perspective of seeing the spectrum activity, you might want more. An interesting approach might be to look at putting just a little bit more of the video processing into the FPGA. So that would mean you'd need the noise blanker, the FFT, and the thing that essentially converts FFT outputs to pixels. An interesting approach might be to look at whether we could use some of the codes that will synthesize from C to straight to FPGA, and Xilinx do provide programs for that now. So it might be possible to take the same code that is currently in the WDSP suite, for example, and make that run on the FPGA. That would take a chunk of the processing away from the microcontroller and leave that to focus on the audio processing. One of the other questions towards the end of the list was about, sorry, I can't easily look at the questions now that I'm speaking again. There was a question about whether I'd been able to use entirely Xilinx IP or had to provide some of my own, as Pavel Demin did. Well, you've seen in the presentation, there are a few tiny bits of Verilog code that I had to use to put the frequency word into the DDS example. So you're converting from a from a constant value on a bus to generating an AXI 4 stream. It's only a very few lines of code, but I did need to have things that do that, and mine do exactly the same as Pavel Demin's versions. If you look further into the radio, you'll probably want to interface to a codec, and just as Pavel Demin did, I had to write things to transfer data to and from the audio codec. There is Xilinx IP for that, but it turns out the Xilinx IP assumes that the transmitter and receiver will have separate clocks rather than a common clock, and the codec that we commonly use has a common clock for both transmit and receive. And a CW gear that when you press the key down, it ramps the transmit amplitude up and ramps the audio amplitude down, and when the key goes up, it does the opposite, so you get QSK operation. Again, Pavel Demin had created a keyer, and I followed the principles of that to create my own version of it. All of the signal processing flow graph has stayed in the Xilinx IP. It's only the bits around the edges I've had to write my own.
Okay. Great. So there, no problem. Quadrants 2005. Doesn't matter. We're here to answer questions, and of course, it's a good place to ask questions. And I'm very happy that you were giving us so many comments. That's really nice to see, and very good. And I mean, we're kind of handicapped in terms of interactivity anyway. And I'm happy that this kind of discussion can take place, at least in this form, given that because of Corona we cannot meet in the moment. But well, I hope it'll be possible next year again, and then we can have a discussion as we used to in Friedrichshafen, if you want to come to Friedrichshafen. But I've also just before Laurence and we've been talking about possible developments in terms of meeting live or not, how that's going to take place, and so on. And yeah, I think there's always going to be an online option, at least as we're having it now, and maybe we'll have that also in addition in Friedrichshafen next year. So, well, there are some more comments from Markus Müller about the power consumption question. Yeah, and the codec. Laurence, do you want to say a few words again about the codec?
Yeah, so I add an interface to that same codec. It's the same one that's used in the HPSDR products, and it's basically an I2S interface. As I say, the Xilinx IP wasn't quite what was needed, but it is ultimately only a shift register, so it wasn't very difficult to create a suitable piece of IP to interface to that as well. The question about power consumption is an interesting one. As a general principle, power consumption will be lower if the code is executed on the FPGA, but the amount of the power consumed by the ARM processor doesn't seem to be that great when it's running something like HPSDR. So it isn't a real barrier to have the audio processing done using HPSDR in that environment.
Okay. What's the temperature? How hot is it getting? Did you measure that?
Well, I didn't measure it, But this is the Ultra 96. It comes with a big heatsink on the bottom. The processor and FPGA chip in it will be easily capable of dissipating 5 watts or more. But it's a 5 million gate FPGA. I haven't used more than 5 to 10% of that. So I'm not stressing the FPGA in terms of either the clock rate, which will cause the temperature, increasing that will make the temperature go up, or the amount of processing I could have in it. So I've not found it hot to the touch.
Okay. Yeah, that's
the amount of processing I could have in it. So I've not found it hot to the touch.
Yeah, Michael is there. Hello, Michael.
Yeah, that's the amount of processing I could have in it.
Michael has some feedback loop. Okay, anyway.
Yeah.
So are there any more questions very quickly, because we have 3 minutes left? Otherwise, I would like to finish this slot very quickly. No more questions coming in, I see. Okay. Yeah, so Laurence, thank you very much for your contribution and for answering the questions. And I think this is a really interesting mode we're running. And it works very, very well. And you mentioned in the beginning that you would have some more. There is one more question.
Laurence, I have a question on the power consumption. Maybe you can answer in quick. You had some experiments with RedPTIA. You made some experiments. Did you experiment with Pluto SDR? As Pluto SDR is in a RedPTIA with an additionally mixer for the higher frequencies, and Pluto has a lot of less power consumption than the RedPTIA. Do you know that?
Okay, I didn't know that. I've seen the Pluto, and I know one of my colleagues at work has a Pluto. It's not something I've experimented with. I've really not been focusing on frequencies above what the data converters will support directly. But yes, I've seen it.
Okay. Good. So, okay, thanks for that reply. Thank you again for the wonderful contribution and for the response to the questions in the chats. We need to change the studio in that sense. Yes, thank you very much. Michael is clapping hands.
Thank you everyone for listening.
You're welcome. And hope to see you again
really
next year. Really interesting, highly interesting. Hope to see you again next year. As you mentioned that you have some more things to contribute to us about the interface to the PC. This would also be an interesting topic for next year. I'm very much looking forward to hear that. And so thank you and hope to see you again soon.
Okay, thank you everyone.
Thank you very
Bye.
much.
Thank you.